video, we take a look at different bikes in Moto3, Moto2 and MotoGP. Let's start with the chassis or frame. The chassis for all classes are prototypes. The engines of the MotoGP and Moto3 bikes are also prototypes, but the Moto2 bikes use production-made engine. Moto3 bikes use a 250cc one-cylinder 60 horsepower engine, whilst the Moto2 bikes use a 765cc three-cylinder engine with around 140 horsepower. The MotoGP bikes have a 4-cylinder 1000cc maximum engine capacity that put out around 250 horsepower. The rules in MotoGP specify a minimum combined bike and rider weight in Moto3 of 152 kilos and 270 kilograms in Moto2. In MotoGP, there is only a minimum bike weight of 157 kilograms. The top speeds exceed 245 kilometers per hour in Moto3, 295 in Moto2, and a whopping 350 in MotoGP.
Let's take a closer look at the machinery on the 2018 MotoGP grid. First up, it's the Repsol Honda that will be ridden by Marquez and Pedrosa. The RT213V has a shortened rear exhaust, and the team has also made some changes to the engine to make the power delivery more linear. The most obvious visual difference, however, is the aerodynamic fairing, which the team has run to improve stability and, of course, aerodynamics on the start-finish straight. Next up, Ducati's GP18. The main differences include chassis improvements, whilst the rideability of the engine has been improved, and adapting to a more traditional design of fairing to improve the airflow. The team also has moved the fuel tank position, which affects the geometry of the bike, especially during race trim. Over to Yamaha, and the team have made some changes for this year after 2017 was fraught with inconsistency. The YZR-M1's engine has also undergone some improvements with more power, whilst the Japanese manufacturer have gone for their own and somewhat understated design of aero fairing. Time will tell, however, if this is set to work, but it's going to be an interesting year for the Japanese manufacturer. A turbulent 2017 for Suzuki sees them striving for improvements as they get concessions back this season. They've got a new exhaust and have developed their GSX-RR engine to increase top speed, but also get better acceleration out of the corners. Their aero fairing looks similar to Ducati's, but will it prove to be effective over the course of the season? Only time will tell on this occasion. And finally, we look at KTM, the only team running a tubular steel frame chassis. For this season, the Austrian manufacturer's main changes include an updated swing arm and improved front suspension from in-house supplier WP. Their fairing looks significantly different to their competitors, however, but it'll be very exciting over the course of this year to see if they can move up the 2018 grid. Time will tell, but it'll be very exciting.
In this week's 3D video, we're going to take a look at how a race weekend is organised from free practice Friday to when the trophy is lifted on Sunday. The free practice sessions in MotoGP are 45 minutes long, with the exception of FP4, which lasts 30 minutes. The teams and riders use this time to set up the bike for the circuit, test out tyre combinations, and also try to be inside the top 10 fastest to give them a better chance of qualifying on Saturday. Qualifying 1 or Q1 is all of the riders who did not get inside the top 10 during the free practice sessions, and their aim is to set the fastest lap in 15 minutes. The fastest 2 riders from Q1 will progress to Q2 to join the top 10 during free practice and have 15 minutes to ride the fastest lap. The lap times determine the order starting for Sunday's race. On Sunday, there are warm-up sessions before the races begin, and the races vary in length between 95 and 130 kilometres and normally last between 40 and 45 minutes. The top 15 from each race will score points, with first place taking 25 points, second place 20, third 16 and so forth. And that's what you can look forward to each weekend on MotoGP.
Let's take a look at how MotoGP bikes all 19 circuits on the MotoGP calendar offer different challenges, and as a result the bikes must be geared differently for each track. For example, Austin's 1.2km straight, the biggest on the calendar, will require much longer gearing than for the shortest straight in Misano. Teams have 24 gear ratios and 4 primary drives to choose from, which is set at the start of the season. Primary drives will alter the overall ratio across all 6 gears, whereas the 24 available gear ratios are then for fine-tuning to a particular corner or sector. A circuit which has a lot of short and low gear corners will require shorter gearing to offer faster acceleration, whereas at a circuit where top speed is vital, teams will opt for longer gearing to get the greatest top speed possible. But any combination is permitted as teams search for the perfect gearing at each circuit. And that's how MotoGP bikes are geared throughout the season.
Let's take a look at the technology behind the location tracking of a MotoGP bike, how it works and what it can do. GPS positioning is not allowed in MotoGP, but there are other ways for the bike to identify its location on the track. Using onboard sensors, the bike can measure how far it's travelled. The sensors then transmit information to the ECU, which is reprogrammed for each race and each track, and so can use the data to reset at different points and different sectors on the circuit. The bike location can be used for corner-by-corner electronics, where the ECU will deliver settings best suited to the corner that the bike is on, controlling things like engine torque, traction control, engine braking and anti-wheelie. These adjustments in the electronics can greatly help the riders to get the most out of the bike at each point of the race, especially when decisions need to be made in hundredths of a second. A feature of the MotoGP are the rules for teams and riders, so let's take a look at some of the key elements in the Premier class for 2018. Each rider has 2 bikes, generally set up differently from one another, important in changeable weather. The minimum weight, meanwhile, is 157 kilograms. Looking at tyres, each rider is allowed a total of 22 slicks over a race weekend, 10 front and 12 rear. Each team has a fuel allowance of 22 litres, and in the event of wet weather, the tyre allocation changes to 5 fronts and 6 rears. Engine-wise, there are 3 manufacturers who aren't able to develop their engines mid-season, with Honda, Yamaha and Ducati having 7 per rider throughout 2018. Suzuki, Aprilia and KTM meanwhile have 9 engines per rider this season and concessions available to develop them. Finally, let's focus on fairings. The aerodynamic innovations for this year are limited to 1 per rider, which can be upgraded once throughout the season. However, they are removable should they prefer not to run them. And that's a look at some of the key rules for the 2018 MotoGP season. Let's take a look at the different styles of cornering in MotoGP. Typically when approaching the corners, riders have 2 options. They can choose speed and try to outrun their competition, but risk sacrificing accuracy and control, or they can rely on the brakes and corner as tightly as possible, but lose speed. As we can see, the Movistar Yamaha bike is cornering at high speed, using progressive turning. Releasing the brakes early carries much more speed through the apex, for having a much wider angle through the corner, whilst the smooth throttle on exit helps to maintain a good speed. The Repsol Honda bike here, meanwhile, squares off, relying much more on brakes and acceleration of the bike. The rider releases the brakes later and accelerates hard out of the apex. The Movistar Yamaha rider takes a much wider racing line, going faster through the apex, giving him more time to lean and needing much less grip. The Repsol Honda rider, on the other hand, uses the fat part of the tyre, needing more grip for the tighter angle and timing the lead more precisely. Both types of cornering have their moments, and while some riders and bikes favour a certain style,
let's take a look at the life of the MotoGP engine. Every MotoGP team is allocated 7 engines per rider, or 9 engines for KTM and Aprilia due to concessions. Those 7 engines must get through all 19 Grand Prix and anywhere from 140 to 133 sessions in a single year. All of that track time in 2018 will up to these numbers, given lap distances in each track between 3. All of that track time in 2018 will up to these numbers, given lap distances in each track between 3.6 and 5.9 kilometres, the total number of 1,000 kilometres. It means all 7 engines must cover approximately 12,000 kilometres in a season, with a single engine's life approximately 2,000 kilometres. 2 engines will always be in use at one time between the first and second bite, but once it's withdrawn, it's officially withdrawn for the rest of the season. And that is everything that you need to know about the life of a MotoGP engine.
in this week's 3D video, let's take a look at fuel consumption in MotoGP. As each track is a different length, the teams must carefully calculate how much fuel is used over a race distance. The amount of fuel that a bike uses can be electronically adjusted to fit the circuit, but the teams must use all 22 litres for maximum power, without, of course, running out before the finish line. Naturally, temperature affects the volume of the fuel, with the volume increasing in hotter climates and decreasing in colder ones. As a result, fuel is measured in weight by kilograms rather than by litre. For example, a full 22-litre tank will hold 16.5 kilograms of fuel at 15 degrees Celsius. At 25 degrees, the same weight of fuel would cause the tank to overflow, whereas at 5 degrees, the tank would be only 3/4 full. So the teams have to adjust the amount they use based on ambient temperature. Teams are allowed to cool the fuel by up to 15 degrees below ambient temperature before the race to fit more in the tank, which leads to more power. Let's take a look at parts mileage in MotoGP. There are around 2,000 parts on a MotoGP bike, and around 200 of them need changing at various intervals due to wear and tear. Let's take a look at some of the more important ones. Over an average race weekend, from FP1 to the end of the race, a rider can put in around 500 kilometers on their bike. Over this period, the teams have to change the oil, water and chain. Every 1,000 kilometers, the teams have to replace the sprockets, clutch plates and the carbon brake discs and pads. Every 1,200 kilometers, the teams must completely replace the wheels. Every 2,000 kilometers, or around 4 races, teams must completely remove and replace the engine. Every 4,000 kilometers, or around 8 races, just under half a GP season, teams have to replace the handlebars and seats. After around 9 races, half a GP season, the teams replace the bike's frame and swing arm. That's part mileage in MotoGP.
Let's take a look at how MotoGP bikes are keeping. All 19 circuits on the MotoGP calendar offer different challenges, and as a result, the bikes must be geared differently for each track. For example, Austin's 1.2 km straight, the biggest on the calendar, will require much longer gearing than for the shortest straight in Misano. Teams have 24 gear ratios and 4 primary drives to choose from, set at the start of the season. Primary drives will alter the overall ratio across all 6 gears, whereas the 24 available gear ratios are then for fine-tuning to a particular corner or sector. A circuit which has a lot of short and low gear corners will require shorter gearing to offer faster acceleration, whereas at a circuit where top speed is vital, teams will opt for longer gearing to get the greatest top speed possible. But any combination is permitted as teams search for the perfect gearing at each circuit. And that's how MotoGP bikes are geared throughout the season.
Let's take a look at the exhaust systems on a MotoGP bike, how they can be modified and what the results of those changes can be. The exhausts have 2 main purposes. Firstly, to remove the waste gases from the engine and also to draw air and fuel into the cylinder for burning. Believe it or not, but the exhaust can have quite a profound impact on the performance of the bike. It can increase the power within rev ranges. As a result, this can change the throttle feel for the rider, making the throttle more or less smooth or sensitive. The length, width, and even the shape of the exhaust can be modified, affecting the flow of air and gases to and from the engine, allowing more or less exhaust fumes to escape faster or slower, and increase or decrease the back pressure and upstream. The exhausts are made from a titanium alloy that's extremely heat resistant. This is important because at high speeds, exhaust gases can reach 1,000 degrees Celsius. MotoGP teams are allowed to change their exhaust about 8 to 12% faster than the front wheel, depending whether we're on a straight, accelerating, or cornering. Also, the grip level and the tyre softness. Let's take a look at an example. If the bike is travelling at 330 km per hour, the front wheel spins accordingly. The rear wheel, however, is spinning 12% faster at 369.6 km an hour. So we get that forward thrust that we've been talking about. And that's rear wheel spin in MotoGP. Let's take a look at downforce and top speed in MotoGP and some of the trade-offs that must be made when deciding whether to ride with or without the aerodynamic fairings. Top speed can only be achieved when the riders open up the throttle. Depending on whether they're riding with the fairing depends just how fast top speed is. The standard fairing allows for a higher top speed and greater agility. This has to be weighed up against reduced stability when braking. The aerodynamic fairing, on the other hand, provides more downforce, reducing the wheelie and increasing the front tyre contact whilst improving stability when braking. The shape of the fairing can have a significant impact on the drag, which can be used to the rider's advantage. The standard fairing creates less drag and creates less downforce, which could lead to more wheelie when accelerating. The aerodynamic fairing, on the other hand, creates more drag but directs it to keep the front tyre on the track. Ultimately, it's the aerodynamic fairing that keeps the wheels in contact with the asphalt for greater. In this week's 3D video, we take a look at leaning and turning in MotoGP. The rider leans into a turn to create a centripetal force, forcing the bike through the turn and counteracting the centrifugal force, which pulls the bike and rider outwards. The rider starts the turn by counter-steering. Contrary to what you might expect, the rider actually steers in the opposite direction of the turn, causing the bike to lean into the corner. If the rider didn't do this and turn the handlebars into the turn without leaning at such high speed, they'd be thrown outwards due to the centrifugal force, like a high side and undoubtedly crashing. Once committed to the turn, the rider continues through it, leaning, often using their knee and even elbow for stability, and begins to steer into the turn. The amount that the rider will lean depends on how tight the corner is, how fast they are going, and the grip levels of the tyre and surface. And that is leaning and cornering in MotoGP. In this week's 3D video, we take a look at anti-wheelie in MotoGP. We're going to look at 3 fundamental ways of preventing the bike from wheeling, looking at the electronics, the fairing, and the rear brake. Starting with the electronics, or ECU, on the bike, sensors detect when the bike is beginning to wheelie and send information to the ECU. The ECU then talks with the engine, briefly cutting the power, and then letting it increase again as the front wheel lowers back down. Now, with the fairing, teams use an aero package which, like a spoiler on a car, directs the air upwards, therefore pushing the bike down, almost the opposite of the wings on an aeroplane. The faster the bike is going, the more downforce is created. And finally, with the rear brake, the riders can apply the rear brake via the foot pedal when accelerating, slowing the bike down slightly so that the front wheel lowers back down. Teams and riders can mix and match these methods as needed, and that is anti-wheelie in MotoGP. In this week's 3D video, we take a look at anti-wheelie in MotoGP. We're going to look at 3 fundamental ways of preventing the bike from wheeling, looking at the electronics, the fairing and the rear brake. Starting with the electronics or ECU on the bike, sensors detect when the bike is beginning to wheelie and send information to the ECU. The ECU then talks with the engine, briefly cutting the power and then letting it increase again as the front wheel lowers back down. Now, with the fairing, teams use an aero package which, like a spoiler on a car, directs the air upwards, therefore pushing the bike down, almost the opposite of the wings on an aeroplane. The faster the bike is going, the more downforce is created. And finally, with the rear brake, the riders can apply the rear brake via the foot pedal when accelerating, slowing the bike down slightly so that the front wheel lowers back down. Teams and riders can mix and match these methods as needed, and that is anti-wheelie in MotoGP. Let's take a look at the different styles of cornering in MotoGP. Typically when approaching the corners, riders have 2 options. They can choose speed and try to outrun their competition, but risk sacrificing accuracy and control, or they can rely on the brakes and corner as tightly as possible, but lose speed. As we can see, the Movistar Yamaha bike is cornering at high speed, using progressive turning. Releasing the brakes early carries much more speed through the apex, but having a much wider angle through the corner, whilst the smooth throttle on exit helps to maintain a good speed. The Repsol Honda bike here, meanwhile, squares off, relying much more on brakes and acceleration of the bike. The rider releases the brakes later and accelerates hard out to the apex. The Movistar Yamaha rider takes a much wider racing line, going faster through the apex, giving him more time to lean and needing much less grip. The Repsol Honda rider, on the other hand, uses the fat part of the tyre, needing more grip for the tighter angle and timing the lead more precisely. Both types of cornering have their moments, and while some riders and bikes favour a certain style, a rounded rider will be adept at both. Let's take a look at traction control in MotoGP. Traction control is important to keep the bike's wheels in contact with the track and provide as much grip as possible whilst preventing oversteer and high-siding. The inertial platform in the IMU detects the lean angle, while sensors in the wheels detect the amount of wheel spin, indicating how much grip the tyres have and how much contact there is with the track. If the rear wheel loses traction, meaning the grip drops and the wheel starts spinning faster than the front one, the back wheel can swing out wide, causing oversteer. Should this happen, the sensors talk to the ECU, which cuts the power by cutting one of the cylinders, closing the electronic throttle, or reducing the ignition timing. This is important because if the bike were to suddenly regain grip, it could high-side, causing a crash and potentially injuring the rider. The teams can tailor the traction control to each rider and bike, as well as customizing it for every turn. As the grip decreases due to tyre wear, the speed, or the nature of the corner, the traction control increases the traction to maintain contact with the track. And that is traction control in MotoGP. Let's take a look at oversteer and understeer in MotoGP. What is it, what's the difference, and what does it do? Understeering and oversteering are ways of manipulating the bike throughout the turn. Riders can adjust their steer angle, oversteering or understeering to compensate for speed or to line their bike up for the next section of the circuit. Understeer is when the side slip of the tyre is greater than the rear, pushing it away from the turn. Here the front tyre has significantly less grip than the rear tyre. The problem with understeer is the risk of running wide, as it's hard to turn and correct. Sliding the front wheel increases the wear on the tyre and the rider could risk crashing. Oversteer is the opposite and is much safer, when the rear tyre slides out away from the radius of the turn more than the front wheel. The front tyre maintains much more contact with the asphalt than the back. Oversteering can help the rider with turning, keeping them tight into the turn and straightening out from the apex faster using the throttle and electronics. The bike's traction control can help riders recover their control of the bike and avoid crashing. Let's take a look at the front springs of the MotoGP bike, how and why teams might change them, and what the effects can be. Common suspension rates in MotoGP go from 8.5 newtons per millimeter being the softest, up to 10.5 newtons per millimeter on the harder end. MotoGP riders may choose to have a combination of spring stiffnesses in their front forks. Stiffness of the springs is crucial because if the front shocks are too soft, the bike risks dropping too far forward when the riders hit the brakes. On the other hand, if the springs are too hard, the pressure from braking gets transferred onto the front tyre and causes a lot of wear very quickly. The front fork is assembled as a single unit and the two springs work in unison. Teams can change the springs really fast, typically taking less than 2 minutes. Riders can choose to combine springs in the front fork to achieve a more precise overall stiffness. That's how and riders choose their suspension stiffness in that front fork. Let's take a look at what the steering damper is and what it does on a MotoGP bike. The bikes in MotoGP have a short wheelbase and aggressive steering geometry, which is great to help the riders change direction quickly, but can cause instability, uncontrolled movement and wobble when accelerating. The steering damper is connected to the handlebars and the front fork and stabilizes the steering, preventing uncontrolled movement. The damper can be adjusted to suit the rider's feeling, giving them more or less damping, making the bike more or less reactive to sharp steering movements. With less damping, the bike steers more freely. The rider gets more feedback from the bike, but that can also be a downside as the stability decreases. When accelerating, the rider has much less control of the bike, which could lead to wobble with serious consequences. With more damping, the rider has to work more to steer through the corner, but gets much less feedback. More damping does, however, provide more control and reduces the risk of wobble when accelerating. Round 15 of the 2018 MotoGP World Championship takes us to the Chang International Circuit in Thailand for the very first time. Racing at a new track can be difficult for the team to set up the bike. What we do know though is that in Thailand it's hot and humid. The teams can therefore increase the size of the carbon brake discs to 340mm, allowing them to keep cooler. If the rider already uses a 340mm discs, then teams can add airflow intake to direct the air to the brakes and keep them cool. The grip level is a big question mark for the Chang International Circuit, so the teams will be trying out different suspension hardnesses to improve the grip. Softer springs create more grip by transferring more of the bike and rider's weight onto the tyres. This can of course affect the wear of the tyres. For the long straights out of turns 1 and 2, as well as the tighter parts of the circuit, the teams might play with the length of the bike's wheelbase and height. Lengthening the wheelbase and lowering the height can affect how much the bike wheelies when accelerating away, but can affect the turning stability. Let's see this weekend how the teams set up the bikes for the PTT Thailand Grand Prix. Let's take a look at tyre allocation in MotoGP. Each Grand Prix, the riders have a choice of 3 slick tyres, hard, medium and soft. The tyre is made up of layers of different materials to give it certain properties like durability or flex. The rubber compound shell on the tyre is what gives it grip. The tyres are designed to give all manufacturers and riders the opportunity to decide which compound performs the best for their overall package, giving optimum grip, control, durability over race distance. Each rider is given 10 front tyres and 12 rear tyres over a race weekend. They have a mix of hard, medium or soft, and how they use their allocation depends on the demands of the circuit. The 2 riders who go from Q1 to Q2 get an extra front tyre of their choice and rear soft tyre added to their allocation. In the case of rain, the teams get 6 front and 7 rear tyres, and the compounds are extra soft, soft and medium. And those are the tyre allocations in MotoGP. Take a look at the brake lever protector in MotoGP. The brake lever protector is there for the safety of the riders and is mandatory in all of the classes because racing is so tight and the riders get right up next to each other. They do say rubbing is racing. The brake lever is there to stop accidental braking should the riders collide. Without the protector, there could be risk of unintentional braking, which could cause crashes. With the brake lever protector, however, the lever is safe from accidentally being pulled and there is no risk of unintended braking. Race direction will not allow the bikes to race if the brake lever is not completely protected. And those are the brake lever protectors in MotoGP.